Hello everybody, so welcome to the second lecture. We were discussing about uniqueness of spherical metrics with conical points. So that is solutions to this Liouville type problem. So I recall you have Laplace and then you have a nonlinearity of the exponential type, which is in mean field form, so you divide by the total integral and you put a real parameter rho here, and then you have some extra terms which does not play much role. So this is on S2, and I study uniqueness depending on this parameter rho. If you want to get back to the original geometric problem of prescribing the Gaussian curvature, you have to choose rho to be a specific geometric quantity. Okay. Second, the function, the weight function k alpha in front of the nonlinearity is smooth and positive, and you have some singular points, and around each point has this form locally. So it's a power 2 alpha j around some points pj, and so you have in general n points. So these are the conical points of your metric. Alright, so we were talking about uniqueness. So uniqueness is expected for rho small. So indeed the uniqueness holds so the two known results are the following one. So the first one is about say the case where the parameter rho is strictly smaller than the geometric value, which I recall here. So in this case, if you have at most two conical points, then you have uniqueness of solutions for this problem. So the idea here is the following. You start from solutions on the sphere with at most two conical points, and then you project down the solutions to the plane, and you show that these solutions need to be radial, and then you show that radial solutions are indeed unique. Okay, so this is the argument. So you pass through the radial solutions, so you simplify first the problem and then show uniqueness. And then we have a complementary result, which is about the geometric case. So here we are really talking about spherical metrics, and we need to assume that we have at least three conical points, and all of them have negative alpha j here. Okay. So again, this is proven to be, you have just a unique spherical metric with that property. And the method is completely different, so you cannot pass through radial solutions anymore, and you use some algebraic geometric approach, which is quite different in spirit. So the aim of this talk is to present a new method to address these problems and to unify the approach and to complete this uniqueness program. So first of all, let me give a remark about this second result, so about the geometric case. So why we need to assume these properties? So first of all, if you do not have singularities, or you do have two singularities, then this problem solutions are completely classified, and you have a whole family of solutions, so uniqueness does not hold. On the other hand, for if you have just one conical point, so you have one conical point and constant Gaussian curvature outside of it, so this is the teardrop surface, and it's known that this does not exist. Okay, you cannot have a teardrop with constant curvature. So you see, you cannot drop the first condition. How about the second one? So taking alpha j all negative. So indeed, it is shown that uniqueness in general fails if some of this alpha is taken to be positive. So somehow the second geometric result is indeed sharp. Okay, so our result is the following, so which is in collaboration with Daniele Bartolucci from Rome, Changfeng Gui from Texas, and Amir Mardavifam from California. So we again take all alpha j to be negative, and suppose you have n conical points. Then this is the result. So if you have any number of conical points, then you can show that there exists at the most one solution if the parameter is strictly smaller than the geometric case. Otherwise, if you have at least 3, then you have just a unique spherical matrix. So the second one is exactly the result that I was pointing out in the previous slide. So the aim here is to give a unified approach to this problem. So how to address this? So let's see the idea of the proof. So the main tool here is the so-called sphere covering inequality, which was obtained in the regular case by Gui and Mardifam, and is as follows. So consider two regular solutions for this Liouville type problem in a domain. So we are now in a flat, bounded, smooth domain. Okay. So under extra assumptions, which I will not recall here for simplicity, so suppose that you have two different solutions which agree on the boundary. Okay, for this problem. So what you can show is that the total integral of the sum of the two solutions is bounded from below by 4 pi, which is exactly the area of the sphere. So the geometric interpretation of this is as follows. So each solution of this Liouville problem gives you a portion of a surface which some prescribed Gaussian curvature. So what the result is telling you that is that the total area of this surface made up of these two solutions is bigger than the area of the sphere. Okay. So this is why the result is referred as the sphere covering inequality. So this holds in full generality. So what we proved is a singular version of it. So suppose you have two singular solutions. So we add some singular term in front of the nonlinearity, with the same assumption as before. So you have two different solutions which agree on the boundary, Then what you show is the singular version, so the total area of the sum of the two solutions will be bounded from below now from the area of the American football. So the picture is as follows. So you have two singular surfaces, so you have some conical points which are given which are connected in relation with the two solutions, and then you show that the total area is bigger than the area of the American football with some proper angle here, which I will not go into details. You can actually prove more, as for the regular case. You have a rigidity result, and you can show that the equality here holds if and only if you are in this, say, American football case. So really, if you have equality, then the two surfaces has to be two spherical cups of two complementary spherical cups of the American football. Alright, so once you prove this, so I will give a brief idea how to prove this result. So once you have this result, let's see how to get uniqueness. So let me start with the regular case, and we start with the case where rho is strictly less with less than the geometric case. So in the regular case, the geometric quantity is just 4 pi. So we are now in the regular case with rho strictly less than 4 pi. So the proof goes by contradiction. So supposing you have two distinct solutions of this problem, okay? All right, so now let's define so you have two functions, two solutions, vi, and then I just call, I rewrite this quantity, this function, as exponential of 2ui. Okay, so I just englobe all these quantities into just one function here. So this function, of course, is normalized, so you can observe that the total integral of these two functions is just the parameter rho, okay, by construction. So since they are different and they have the same integral, then you need to have at least two nodal regions, okay? So roughly, the picture is like this. You have two nodal regions. So in one region, you have one solution is bigger than the other, and in the other nodal region is the opposite. So in particular, you have two regions on which the solutions are different, and they agree on the boundary. Okay, so the idea is to apply the sphere covering inequality to both these nodal regions. So of course here we are on S2, and the sphere covering inequality is carried out on flat domains, so that there are some steps which I will just neglect for simplicity, and I will just give an idea how the proof goes. So you apply the sphere covering inequality to both regions, and what you get? So the total integral on the sphere of the sum of the two solutions, of course this is just 2 rho, okay, and this is the integral, the sum of the integrals on the two nodal regions, and then on each region you apply the sphere covering inequality, which gives a bound from below of 4 pi. So at the end, this is bounded from below by 2 times the bound 4 pi. Okay, so at the end you get that the parameter rho has to be bigger or equal than 4 pi, and this is in contradiction with the assumption that which we start with rho strictly less than 4 pi. Okay, so this is somehow the very rough idea how the proof goes for the regular case. So how about the singular? So in the singular case you can do the same, but I would like to point out why in the geometric case we need to assume to have at least 3 conical points. So where this assumption pops out. Okay, so let's suppose we are in the singular case, we are in the geometric case, and we have at least 3 singular points, so 3 conical points. So you do the same and you end up by having 2 nodal regions. You apply the singular sphere covering equality to both of them, and so the same argument gives you that 2 times the geometric parameter will be bigger or equal than 2 times the geometric parameter again. Okay, so this somehow is what the singular sphere covering inequality tells you. So this is related to the area of the American football. So you see that if we are in this threshold case, so if we are in the geometric case, still we don't have a contradiction, okay, because here you can have equality and you cannot conclude. So here comes the assumption that you have at least 3 conical points. So these 3 conical points will be somewhere on the sphere. So you may suppose you have 2 in one region and 1 in the second region. So suppose we have, say, 3 conical points. So you have this situation, and here you really need to exploit the full power of the sphere covering equality and the rigidity result. So we know that the equality holds if and only if we are in the American football case. So this means that the equality holds if these 2 nodal regions are indeed complementary spherical cups with 1 conical point. Okay, you need to have the American football here. But this is clearly not possible if one nodal region contains 2 conical points. So this cannot be a spherical cup with 1 conical point. So this means we cannot have the equality. So you need to have a strict we are strictly greater than the American football case. So here we have a strict inequality, and this now allows to get a contradiction. Okay, so you really need to exploit the rigidity result of the sphere covering equality. All right. So this is more or less the idea how you get the uniqueness proof. So in the last part, I would like to show what is the idea of the sphere covering equality, which is the main tool here. So first of all, you need to study what is the how you get the equality case in sphere covering. So the equality is obtained in the following situation. So suppose we are in a radial situation, so we are in a disk BR. Here you can take some explicit solutions which are well-known solutions, which are called the bubbles, so which are just conformal factor of the stratigraphic projection. So you have a whole family of these solutions depending on this parameter lambda. So you move lambda and you somehow move the spherical cap here. So a solution of this problem gives you a spherical cap of the sphere. So if you take now two spherical caps, two complementary spherical caps, so this means you take two different lambdas, so lambda 1, lambda 2, such that they are different, so you have two different spherical caps and they agree on the boundary. Then of course you make the computation and you see that the total sum, the total integral of the sum of the two solutions is the area of the sphere. So this gives the equality in the sphere covering result. All right, so the idea now is in general to make a comparison with this equality case and see that in all the other cases you will have bigger equal than the area of the sphere. So let's see how you make the comparison. So to make the comparison you need isoperimetric inequalities. So let me recall what is the standard isoperimetric inequality in the plane. So you take a domain and what is known is that the length of the boundary squared is bounded from below by 4 pi the area of the domain. So you can lift this on the sphere and you have something similar. So again the boundary squared is bounded from below by the area, but you have to adjust this because now you are on the sphere. So now you can rephrase this in terms of solutions of the Liouville problem, since each solution of the Liouville problem gives you somehow a domain on the sphere. So for any solution of this equation you have something similar. So the area, so the length squared will be controlled now by the area of the domain, which is given by the total integral of the exponential. Okay, so you have the same inequality, the same isoperimetric inequality rewritten in terms of the solution of this Liouville equation. And again, the equality holds if and only if you have a spherical cap. So if and only if the function u is the bubble u lambda, which I was referring before. Alright, so now the idea is the following. Suppose you have a solution to the Liouville problem such that it agrees with the two spherical caps. Okay. Alright, so I have the isoperimetric inequality as before, but I can put in here not the length of the general function u, but you can put the length of these two spherical caps, since they all three agree on the boundary. Okay, we know that the equality now holds if and only if the function u is exactly the spherical cap, one of the two spherical caps. So this gives you a condition on the total area of the exponential. So this you see now everything is fixed here, and you have the total area which is allowed to vary, and so this condition gives you a condition on the parabola. So you see you have minus area squared and then this is less or equal than 0. So the total area, the total integral of the exponential, needs to be in somewhere either here, so less than the area of the smaller spherical cup, or bigger than the area of the bigger spherical cup. So each solution which agree on the boundary with the spherical cups needs to satisfy this alternative. Alright, so let's see how we conclude. So suppose for simplicity you have two solutions on in a disk. One is bigger than the other and they agree on the boundary. Okay, so a simpler situation. So the idea is take now two spherical cups. So you take 2 lambda such that the total integral of the smaller solution agrees, so coincide with the area of the smaller cup. Okay. All right. So so we are halfway to conclude. So the smaller solution has the area of the smaller cup. So we just need to compare the bigger the total integral of the bigger solution. So we need to put in relation the area of the bigger solution with the area of the bigger cup. So the idea is as follows. So you start with the exponential of the u2 and you just rewrite in this form. So this is the smaller solution plus the difference of the two. Okay, and then by construction you can show that there is a relation with this quantity. So the smaller solution will be related to the smaller cup, and you are left with some error term which is given by the difference of the two solutions. So of course this will not be the same, but you can relate the two quantities by some symmetric rearrangement. Okay, so suppose this is really the same. Okay, and so can we compare now this quantity, this area, with the area of this bigger spherical cup? So here we use the alternative because we have that of course this function agrees on the boundary with the bigger spherical cup. So you see on the boundary the two solutions agrees, so the difference will be just 0. So on the boundary this will be just the spherical cup. So this function agrees on the boundary, and moreover the error term is positive. So we have a function which agrees on the boundary with the spherical cups, and it is bigger than the smaller spherical cup. So if we go back here, we cannot be in the first situation, in the first alternative, so we need to be in the second alternative. So we need to have an area which is bigger than the area of the bigger spherical cap. So we can conclude that all this area is bigger than the area of the spherical cap. Alright, and so we are done, because we just collect together these two informations, and we have that so the first solution is the same as the smaller spherical cap. The second solution is bigger than the bigger spherical cap, and we know that this is exactly the equality case, which gives the area of the sphere 4 pi. So this gives somehow the idea of the sphere covering equality in the regular case, and the similar case goes in a similar way. So this is what I wanted to say. So I hope you enjoyed, and I thank you for your attention.